Okay, so welcome to today's central exercise session. We will be discussing sheet number 8 today. And if you had a look at sheet number 8 already, you will have noticed that it is a very brief sheet. That's due to the public holiday we had that week. So there's basically two topics on that sheet. One is Newton's method for optimization, and the other one is the method of Lagrange multipliers for constraint optimization with equality constraints. So as usual, I'd like to post a quick survey to see which of these topics you found more challenging. So I'd appreciate a quick feedback here. Yeah. Okay, maybe we'll give it 10 more seconds. Okay, let's end the survey. And here's the results. So as you can hopefully see, about 3/4 found constraint optimization with Lagrangian multipliers challenging. That's pretty much what I expected. I didn't expect that many problems with Newton's method, actually. But we have problems on both topics on today's central exercise session. So maybe we'll be able to clarify a few problems today. As usual, there is a live chat on chat.tum.de. Please use this channel here, MA9714-CE, for your questions. The chat will be moderated. Today's moderator is Philip Krebs. Philip, would you introduce yourself, please?
Hello. Yeah, a lot of people maybe know me from the tutorial.
Hopefully. Okay, so if you have any questions, just post to the chat, please. We'll either try to answer those right here on the air, or Philip will try.
Your mic is.
Is it better now?
Yeah.
Okay, great. So sometimes it seems to drop volume. If that happens, just please interrupt me anytime. Usually reconnecting seems to help. Okay, good. So I'd say let's start right away with our first problem. First one is on Newton's method. And the second one will then be on the method of Lagrange multipliers. Okay, so that is problem 8.4. We have given a real valued function. Of course, for optimization, we always need a real valued function, in this case defined on R2. And the function is defined as f of x1, x2 is simply the sine of x1 times x2. So that should be a pretty simple function. And basically, we are being asked to execute Newton's method on that function with a given starting point. To do that, we first have to compute the gradient and the Hessian of that function, and that's part A of that problem. Okay, so for the gradient of f of x1 and x2, we need to differentiate with respect to x1 first. The derivative of the sine function is the cosine function. So the derivative of that outer function is cosine x1, x2. And then we need to apply chain rule. And we need to multiply this by the derivative of the inner function, which is x1 times x2. So if we're differentiating with respect to x1, then the derivative of x1, x2 is just x2. Okay, and for the second coordinate, we take the differential with respect to x2. That outer function is the same, so we again get cosine x1, x2. And this time the derivative of the inner function is x1. Okay, so that's our gradient. And for the Hessian, Let's start with the first row of the gradient and differentiate that with respect to x1 first. Then what happens, basically the same as we just did. Again, there's no x1 outside of that cosine expression. So we can just start by differentiating that. The derivative of the cosine is the negative sign. And again, we need to then multiply with the derivative of that inner function, okay? So what we get is the negative sign of x1, x2 times differentiating this expression with respect to x1 again yields x2, and we still have that x2 out here. So together that is x2 squared. Okay, so that's this first entry here. For the second entry in that row, we again take this expression and now we differentiate with respect to x2. And that means we need to use product rule now. Let's first differentiate this part here. That simply yields that cosine. So we get cosine of x1, x2. And then we add the derivative of this cosine expression times x2. We already computed the derivative of that cosine expression. Basically, again, we get minus the sign, and then again, we have to multiply with the derivative of that inner function. So we get something minus the sine of x1, x2. Differentiating that inner function, we now have to differentiate with respect to x2. So that derivative will be x1, and we still have this x2 here. So that's times x1, x2. Okay, so this is the entry in row 1, column 2 of the Hessian. That function that we have here is continuously differentiable everywhere. So by Schwarz's lemma, the entry here in that position will be the same as this one here. So we can just copy that. So that's cosine of x1, x2 minus sine of x1, x2 times x1, x2. And for that last entry, we need to differentiate this entry here now with respect to x2. Again, the only x2 is inside of that cosine. So we differentiate the cosine first. That's a minus sine of x1, x2. Then we multiply with the derivative of that inner function, x1, x2. Differentiating that with respect to x2 yields x1, and we still have that x1 out here. So what we get is times x1 squared. Okay, so that is the gradient and the Hessian of that function sine of x1, x2. Any questions so far, Philip?
No, there aren't.
No. Okay, great. So let's go on to Newton's equation. So we now have the gradient and the Hessian. And in part B, we are asked to write down the Newton equation for the starting point, x0 equals, or is it 1? No, pi 1, like this. Okay, so to write down Newton's equation, what we first need to do is we need to compute the gradient and the Hessian at that point, and then we're ready to write down the equation. Just as a little reminder, Newton's equation, that gives us a direction that we want to step into. So what we do to compute that direction is we take the Hessian at the current point, in this case x0, and we'll compute a vector v such that hf times v is the negative gradient. So that's Newton's equation. So to write that down for this particular function and this particular x0, all we have to do is we need to compute this value and this value here. Okay, so let's do that. starting with the gradient at pi and 1. So x1 is pi, x2 is 1. So that means x1, x2 is pi. So this expression here is pi. The cosine at pi, you will hopefully remember roughly how the cosine looks. So very roughly, the cosine is this function here that starts at 1 here at 0. Then the first 0 is at pi over 2. This here, that's -1. That is pi. That is 3 pi over 2, and so on. Okay, so the cosine at pi is -1. So this expression, whoops, sorry, this expression here is -1. And then we just multiply with x2, which is 1, and x1, which is pi. So we get -1 and minus pi. Okay, similar for the Hessian here. Pi and 1. So we established the cosine already. Let's make a drawing for the sine as well. So very similar to that. The sine is just basically the shifted version of that. So again, here's 1, here's -1, here's 0. This is pi over 2. This is pi. This is 3 pi over 2. So for pi, the sign of pi is 0. And we already established that x1, x2 is pi. So this expression here becomes 0, this sign expression. So that means that entry is 0. The same is true for this entry here, that also is 0. And of course also for these two parts here, okay? So we have a 0 here, we have a 0 here. And here we only have a cosine part that remains, this one and this one, and that's the same. So cosine of pi, we already computed that. You remember that is -1. So we get a -1 in these two positions. That is the Hessian. And that means we can now write down Newton's equation. So Newton's equation thus becomes, so what we get here is the Hessian. Let me write that down once more. The Hessian of pi and 1 times v equals minus the gradient of pi and 1. So what we get is 0, -1, -1, 0. That v is a vector of appropriate dimension. So in this case, 2-dimensional, v1, v2. And that is the negative gradient, so 1 pi. Okay, so this is Newton's equation. Philip, any questions?
No,
Good.
there aren't any.
Great, so part C probably asks for the next iterate, right? Right, yeah. Okay, so for part C, the question is to determine the next iterate of that Newton's equation. So what we do is we determine x1 by starting at x0 and then just adding the v that we have to compute through the equation above. Okay. So what we need to do first is we need to solve Newton's equation. That is a very simple equation. So what we have here is basically the two equations: minus v2 equals 1 and minus v1 equals pi. So no need to invoke Gaussian elimination or something like that, because you can directly write down v. Obviously, v is just pi and -1. Sorry, minus pi, of course, minus pi minus 1. Okay, and that means x1 is then x0 plus v, or x0, that was pi 1 plus minus pi minus 1. So that's a very nice result. We get 0, 0 as the next iterate here. Okay, so this is our next iteration. Let's have a very quick look at the function value before we take questions. So the idea was to minimize the function through Newton's method here. The function value at x0 was pi and 1, so that's the sine of pi times 1, that's 0. The function value at this new iteration point here is sine of 0 times 0. So that's also 0. So in this case, nothing has changed, right? We got a new point, but we didn't get a better value. Questions, Philip?
There are no questions.
Still no questions.
Still
okay.
no questions.
Yeah, great. So let's do D. And then we're done with that. It's a short one. So D is asking the question, is that new iterate a global minimum of F? And well, you remember the graph of the sine? It basically looks like this here. We currently have a function value of 0. So these are the roots of the sine function here. And you can also see that there are values of the sine function that are below 0. So the question is, can we reach those? And if we can, of course, the current point is not a global minimum. On the other hand, if we could not reach any of those points, then there would be a global minimum here. In this case, we have the sine of x1, x2. So the question is, can this product x1, x2, can this take on any value in this interval here from pi to 2 pi, where the sign could get negative? And of course, the ideal situation would be, could we get to this point here, 3 pi over 2? That's the lowest value the sign could have. And of course, it's easy to get there. Yeah, so for example, let's try setting x star to something where the product is 3 pi over 2. For example, let's say we set this to 3 pi and 1 over 2, like this. Then f of x star would be the sine of 3 pi times 1/2, and that's minus 1. And that is less than 0, okay? So obviously, x1 is not a global minimum. Okay, so even if you compute the gradient, by the way, at the point x1, so the gradient at 0, 0, remember the gradient was, where is it? Here's the gradient. Of course, if you enter the point 0, 0 here, then that gradient becomes 0 as well. Okay, so that is a stationary point. But it's not a minimum. And not a maximum either. Yeah, not even a local one. Okay, so the gradient in being 0 is not a sufficient condition for the point that you have being a local minimum or maximum, and certainly not for it being a global minimum or maximum. Questions?
There is a question about C.
Okay.
Aren't we supposed to try and get the function value lower than 0? But I think the question is just asking for one step.
So actually it would be nice to get the function value lower than 0. That's the whole point of this. Yeah, you're right. Problem here is twofold, actually. So the first problem is Newton's method might work or it might not work. That depends a lot on how the function looks like. So that is still a heuristic. It might get us closer to a minimum, or it might even get us to a minimum, but it's not guaranteed to do anything of that sort. It could even get us function values that are worse. Second part, for Newton's method, we did not do a step size. We just computed that step v, and then we added that, because the rationale behind this is we're computing that v such that we get to the minimum of the second order approximation of the function at the current point. And the hope is that this is a good second order approximation and that we will get a minimum that way. But of course, again, that's nothing that is guaranteed. And it would be easy to add a step size to that Newton's method here. So if you do that, then you would compute x1 by adding something like lambda v, and then try to find a lambda that works well. Could do that basically in the same way as we did for gradient descent. But again, you're not even guaranteed that this direction that you're getting actually does something useful. It could even be that, so basically what you do is you approximate the function locally through something that is basically a parabola. And if you're in luck, then this parabola, something looks like that, like a cup, and we'll compute the minimum of that cup. But of course, it could also be that it looks like this, like a dome, right? And then that same step will lead us to the apex of the dome, which is then actually a maximum of that approximation. We don't check for that anywhere here. Of course, that's something that obviously you should also do if you're taking this seriously. You should check if actually the approximation will give you a minimum or a maximum. And if it gives you a maximum instead of a minimum, then obviously Newton's method might not be that good an idea here. You might try other methods. Yeah, but Newton's method as we did it in the lecture works just like this, and it's not guaranteed to give you anything usable. Does that answer the question?
I think so. He just asked, so he has now to change the step size.
That's one thing that you could do. You could try changing the step size, yes. But actually, if you have that dome-like approximation here, then that wouldn't help, right? Because you would that direction would steer you in a direction that increases function values. Even if you take a very small step, you would still not get a decrease, maybe.
Okay.
Yeah, it's not guaranteed. So maybe the direction is plain wrong. And of course, you could work on that by fiddling. So there are methods that try working on that by fiddling around with the Hessian matrix and replacing that by something similar, but positively finite, so that you are guaranteed to get a parabola that is shaped the right way. But that would lead too far for this course. So that's why I chose to omit that.
Okay. Someone else is asking how he knows which function does work for the Newton method. Or
you
on
know which function does work, you don't. The simple answer is you just don't.
Okay. Another question, how we get x star in question D.
How do we get x star in question?
How we set x star.
Basically, all we have to do here in question D is find a value of x that yields a function value that is below 0. So we can prove that the current point cannot be a global minimizer. And by looking at the graph of the sine function, we can see that, of course, there are points of the sine function where the function value is below 0. The only question is with this function f here. So f, remember, f was defined as the sine of x1, times x2. So the question is, can we get function values that are less than 0 here? And we can get those if we can steer this argument here in the middle somewhere into that interval where we have those function values. So basically, the only question is, can we find x1, x2 such that the product of those two is in this interval? And of course, the obvious choice would, if we can, would be to get to this point here, 3 pi over 2. And then I'm just guessing x1, x2 values that do exactly that. Of course, that's not the only possible guess. There's lots of possibilities here. Okay.
Another question is if there is any other approach in D to find out that x1 is a minimum.
X1 is not a minimum.
Yeah, if it's a minimum or not. If there's any other approach.
So one other thing I could think of is you could try, the gradient doesn't help you here. Well, what you could always do is, of course, you could try and look at lines originating at x1 and then examine the different directions and see if there is a descent direction somewhere. But all I can think of is a lot more work than this one here. And a lot more complicated. So I don't see an obvious, easy method other than this one.
There is, can we say that -1 is the global minimum of the sinus function?
Yes, -1 is the global minimum of the sine function, yeah.
Okay.
But there's not a unique minimizer here, obviously, because the sine function is periodic. So 3 pi over 2 is a minimizer, but it's not the only one. You know, the sine function continues in the same way like this here, yeah? So that minimum is achieved again here, 2 pi's to the right, and then also 2 pi's to the left, and so on, yeah? So the unique minimum is -1, but the minimizer itself is not unique.
Another question, could we say that it is a stationary point, but because the Hessian is indefinite, we cannot say that it is a minimizer without looking at the function itself like we did and see that there is a different value?
Yeah, right. So the gradient is 0, so this is a stationary point. And you know that for stationary points, we try to characterize them into local minima and local maxima by looking at the Hessian. And if we have a look at the Hessian, then what we find is that the determinant of this first leading principal minor here is 0. So none of our criteria work. If this had been positive or negative, then we could hope for a positive or negative definite matrix. That's not the case here. Okay, so we cannot characterize this point as a minimum or a maximum. And it's not actually.
Okay, the last question is also about D. We just have, because we have a sinus function with the function values. I'm sorry, it's so much. We cannot easily know where we could possibly have a lower value or a higher value of the function. But I think we just have to put in the numbers.
I'm not sure if I understood.
I'm not sure what he meant. It's very long. But so then we are fine.
The function itself is pretty easy. I mean, the outer function is a sine function, and we know exactly how the sine function behaves, right? So we can know whether there is a point with lower function value or not. The only remaining question is, what about this inner function? Is it possible to achieve such a point through that inner function?
Okay. Yeah. So he just asked for me to read out the question. But we just can answer D because we have a sine function, right? With the function fx is 2 multiplied with x1 multiplied with 4x2, I guess. We can easily know where we could possibly have a lower or higher function value.
So if instead of the sine function, we have a function like this here, then of course still we could say, well, the function value at the current point, 0, 0 is obviously 0. So if you want to know whether this is a global minimum, then the question is, are there points with lower function values? And of course there are points with lower function values. Again, by just looking at the function, let's say we take 1 and -1, then we have 2 times 1 times 4 times -1, that's negative, right? So that's better in terms of minimization. Again, of course, you have to look at the function. You have to somehow know how that function behaves, at least locally. Yeah, if you wrote down a very complicated function, then I wouldn't be able to do that anymore. But in this case, you are right that we cannot easily say where the minimizers are. And actually, there are no minimizers here. Yeah, we could say that, but it's not easy to find the minimizers. For the sine function, that is easy, but we don't actually have to find the minimizers. So the only thing we need is we need to find a point where the function value is strictly less than 0. And then we have shown that that point 0, 0 with function value 0 cannot be the global minimum. That's the whole point here. I'm just getting at the global minimum because I can.
Okay. And the last question, someone asked why -1 is smaller than 0 in D, and what you mean with this.
What?
I'm not sure where he is. So why -1 is smaller than 0?
So this, probably this expression here, I'm not quite sure.
And I think he is mentioning something.
So this is -8, of course.
More to the starting. I'm not sure. I think the first line here. Yeah.
Okay, so if I take this x star here that I somehow guessed by looking at the sine function, then I can see this product here, 3 pi times 1/2, that's 3 pi over 2. And because we know how the sine function behaves, this is this point here, we know that it takes on a value of -1 at this point, right? So this is equal to -1. And I hope we can all agree that -1 is less than 0.
Okay. I wasn't sure if he meant that. And the last question is about the exam. If there is a question like C, if they have to change the step size or not.
That might actually be a nice exam question. I haven't thought about that yet. But
Okay.
actually this question 8.4, this is coming straight from an exam. So that's from the exam for the summer semester 2017, actually, one of the 2 exams there. That's an exam question. And many people got that right, apart from part D, if I remember correctly. So that seemed to be complicated. So last part, people often argued with the gradient, and of course you don't get anywhere if you argue with the gradient.
Okay, that was the last question.
Okay, good. So let's go on with the method of Lagrangian multipliers then. CF5. So in CF5, we have a set C. That set C is defined as all x in R2 with the norm of x minus the point 1, 2 is exactly equal to 2. And it even says what that point is supposed to be. That's a circle around the point 1, 2 with radius 2. And we're given a point P. P is 5, 0. And the task is to find a point on the circle that is closest to P. And of course, you should do that using the method of Lagrangian multipliers to do the computations. So quick look at the setup that we have here. So basically it looks like that. We have this point 1, 2. Let's see, here's 1, here's 2. So that's about here. This is 1, 2. And then we have a circle of radius 2 around that point. So here, here, roughly here, and here. So that is very roughly that set C here. And we have a point P. And that point P is here at 5, 0. And we're asking for a point on the circle that is closest to P. Okay, so intuitively, the right solution should be somewhere there. Yeah, on that line, as close as possible to P. And let's see if we can also find that out computationally using the method of Lagrangian multipliers. What we have to do first is we have to reformulate that problem if necessary to get it into that framework that we know. And for that we need an objective function. There's no explicit mention of an objective function here, so that's the first thing we need to take care of. What's the objective function here? Well, obviously we want to find a point on C that minimizes the distance to the point P. So the distance to the point P, that should be the objective function that we want. Distance to P. So if we have a point x1, x2, then the distance to P is measured by simply taking the norm of x minus P. That would be the distance, right? So this vector here. This is x minus P, or the length of that vector is x minus P. That's what we want to minimize. Now, that norm, unfortunately, is pretty complicated. So we have x1, P is the point 50. So this is the point x minus P, and that means the expression that we have to minimize is the square root of x1 minus 5 squared plus x2 squared. Right, so that's the objective function. And as a simple rule, if you can make your lives easier by changing the objective just a little, or also changing the constraints just a little so that they mean the same thing but look differently and maybe easier, then you should do that. And the obvious thing we could do here is we could just square that expression here, yeah? It doesn't make a difference whether we minimize the square root of something or the actual expression under the square root. The square root is a continuous function and it's monotonously increasing. So that means the square root is minimized exactly if this expression is minimized. Okay, so that is minimal if and only if that inner function here, x1 minus 5 squared plus x2 squared, is minimal. So that means let's take this as the objective and forget about the square root. So let's take f of x1, x2, defined as x1 minus 5 squared plus x2 squared as our objective. Okay, so that's the objective. And as for the constraint, well, we need to make sure that x is contained in C. So that's the next thing we have to take care about. Constraint or constraints. There's only one constraint here basically that says x has to be on that circle C. Well, that is the case if and only if x minus that 0.12 in the norm is exactly equal to 2. And again, we'll apply the same trick here. That's the case if and only if x1 minus 1 squared plus x2 minus 2 squared, and then taking the square root is equal to 2. Such the definition of the norm. And again, we can just square that whole thing. Right? The right-hand side is positive, the left-hand side is positive, so we don't lose anything if we just take the square of that. x1 minus 1 squared plus x2 minus 2 squared is then 4. Please pay attention to that 2. That, of course, if you square 2, then the right-hand side becomes 4. Okay, so again, this makes things a little easier. Yeah. Remember that we have to take the or compute the gradient and the Jacobian matrix of these two functions here. So differentiating this expression is usually a lot easier than differentiating a square root expression. Okay, so this gives us our minimization problem. So we have to minimize a function f of x1, x2 that is defined as x1 minus 5 squared plus x2 squared, subject to the constraint that a function g of x1, x2, which is defined as x1 minus 1 squared plus x2 minus 2 squared minus 4 is equal to 0. So the only thing that we need to change here is we need to make sure the right hand side is 0. So we're taking the 4 into that function g. Okay, so that's the optimization problem. It's a minimization problem. The right-hand side is 0, so everything's fine for the setup that we have for our Lagrangian multipliers ideas. Any questions so far, Philip?
Yes. Could you explain again how could you simply take out the square root from objective function?
From the objective function that was here,
yes.
right? Okay. So this is the actual objective function. What I do is I say the square root is a function that basically looks like somewhat like this here. So that's roughly the square root function. X maps to square root of x. What is important is it's continuous, so it doesn't do any evil things anywhere. No jumps. And it's increasing. That function is continuous and increasing. Right? And that means the minimum is achieved at exactly the point where this x is minimal. Right? This inner function. If that is minimal, then that whole function is minimal because it's increasing. And that means if I have a function like this, then a minimum of that function will be achieved exactly if the argument, this inner part here, that has a minimum. Then applying a function that is increasing and continuous cannot change that. The value will of course be different, but we're only interested in the minimizers, not the actual minimum yet. Once we have the minimizers, the right x values, then it's easy to compute the corresponding value. Okay?
Next question, can we only take the squared because either way the definition of the norm makes the single component always positive?
I didn't
due to the
that.
squares.
Could you repeat that?
Yeah. Can we only take the squared because either way the definition of the norm makes the single components always positive due to the squares?
Single components always positive. So if those single components of that could be negative, then of course we'd have to make sure that this expression here is still non-negative. Otherwise we couldn't even take the square root, right? If you want the real valued function, and we haven't talked about optimizing complex valued functions, and we're not going to because it's not possible.
Okay.
I'm not sure if I got that correctly, so please ask again if
yeah,
you meant something else.
Okay.
Okay, that's it?
Yeah.
Good, so let's go on. So this is our optimization problem. And we want to solve that using the method of Lagrange multipliers. First thing we need to do is we need to compute the gradient of the objective and the Jacobian matrix of the constraint function. And actually, I just noticed I should name that H to be consistent with the notation in the lecture. So that's actually an H, right? Not a G. I use the G for inequality constraints. Okay, I should change that here as well. So let's go on to compute the gradient of the objective function. So the gradient of f at x1 and x2. That shouldn't be too hard. Differentiating with respect to x1 will give us a 2x1 minus 5 and 2x2 for the x2 part. That's the gradient of f. And then we need the Jacobi matrix of H. So again, for the first column, we differentiate with respect to x1. That will yield 2x1 minus 1. The rest just vanishes. And the second column will be 2x2 minus 2. And again, the rest vanishes. Okay, so that is the Jacobi matrix. And then you remember what we did for the Lagrangian multipliers condition. So basically, what we did was we said a point x star is a candidate for an optimum if it is a point that fulfills the Lagrange multipliers condition. So if there is a Lagrange multiplier that fulfills the following equation: the gradient of f, x1, x2, plus the Jacobi matrix of H at x1, x2, transposed times that multiplier vector, we call that Z, is equal to 0. And this Z here, that is called the Lagrange multipliers. And that is usually a vector, so there is one real multiplier per constraint, right? Okay, that Jacobi matrix has one row per constraint. That means the transposed Jacobi matrix has one column per constraint, and there's one multiplier for each column of that matrix. In this case, our Jacobi only has one row, so the transposed has one column. So that means we only have one multiplier, right? One constraint, one multiplier. Okay, so here we have one constraint, and that means we have one real valued multiplier. So let's just call that Z as well. Okay, if we had more constraints, then we would have a vector Z1, Z2, Z3, and so on, possibly with more than one multiplier, one per constraint. Okay, so that's the Lagrange condition. And that means to find candidate points for optima, what we have to do is we have to find points x and multiplier Z that satisfy this condition. Okay, so find x1, x2, and Z that satisfy this condition. And all such pairs of points and corresponding multipliers then give us candidates for optima. Okay, not necessary that those actually are optima, but that are the candidates. Each optimum has to fulfill this condition here. Okay, so let's apply this to the setting here. Again, we need to satisfy this equation here. And we have computed the gradient and Jacobi already. So what we have to do here is, so we take the gradient of f, that is 2x1 minus 5 and 2x2. And then we add the Jacobi of H transposed. So this matrix here, transposed, that is 2x1 minus 1 and 2x2 minus 2 times Z. And remember, Z is one real value here. It's one multiplier per constraint. Yeah. And that has to be 0, so the 0 vector to be precise. And that means what we have here is basically an equation system with 2 equations. Let's reformulate those a little. See if we can group all the x1s. So here in the first row, grouping all the x1s gives us 2 here. And another 2 here times this z value. Don't forget about that. So we have 2 plus 2z times x1, and then all the rest. So this is minus 5 times 2. This is minus 10. And then we have minus 2 times z. So minus 10 minus 2z. Now let's do the same thing for the second round. Here we try to group all the x2 terms together. That's a 2, sorry. Now, so that's a 2 here, and a 2z here. So we get 2 plus 2z. And then we have 2 times minus 2, minus 4 times z. So that's minus 4z. And that should be equal to 0, 0. Okay, so this is the Lagrange conditions. In addition to that, of course, we also have to satisfy the constraints. So together with constraints, remember the constraints were h of x is 0. Sorry. We get the following equations. So what do we get here? Well, first equation is just this x1, 2 plus 2z minus 10 minus 2z equals 0. Second equation is x2, 2 plus 2z minus 4z is 0. And the third is the actual constraint. Remember that constraint was this here. So we need to write that down as well. That is x1 minus 1 squared plus x2 minus 2 squared minus 4 equals 0. So we have 3 equations, and we have unknowns x1, x2, and z. So we're just going to try and solve for those unknowns. Of course, this is not a linear equation system, so we cannot just use Gaussian elimination. Instead, we have to try and be creative about the solution. So let's see how we can manipulate that system. Let's say we take the first and the second row and we solve those for x1 and x2 respectively. Right? If we do that, we get x1 equals, that is 10 plus 2z divided by, divided by 2 plus 2z. And pay attention. Of course, we can only divide by that expression if it's not 0. So for 2 plus 2z not equal to 0. And that is the case if and only if z is not equal to minus 1. So let's just make a note here that we have to treat this case, z equals minus 1, we have to treat that case separately afterwards. Okay, so from now on, we just assume that's not the case. We can do the same thing for x2. That is then 4z over 2 plus 2z. And again, 2 plus 2z must not be 0. So same case we need to exclude here. Z is not equal to minus 1. And finally, we have that equation here, x1 minus 1 squared plus x2 minus 2 squared equals 4. Let's just get the 4 on the right-hand side. Okay, well, if we have that, then we could just take x1, substitute it here, x2, substitute it here, and then we have an equation that only contains z, and hopefully we can solve that. Okay, so this is the case if and only if the x1, x2 remain unchanged. Just copy those two. Actually, we can even simplify that a little. We can just we can cancel out a 2 here. So that's 5 plus z over 1 plus z. And same here, that's 2z over 1 plus z. Let's make it a little easier. And then we substitute that into the last equation. So that means we have 5 plus z over 1 plus z minus 1. And if we bring that minus 1 onto the fraction, then that means we have a minus 1 minus z here. So this expression squared plus, now we have x2, 2z over 1 plus z, and again, minus 2. Let's get that minus 2 onto that same fraction, and we have to multiply by 1 plus z here, the denominator. Squared, that's 4. And again, don't forget this is only true for z not equal to minus 1. Okay, so this third equation, let's have a look at that one. We can now try and solve that for z. Let's simplify that a little. We get here, we get a 4, 5 minus 1, z minus z, that cancels out nicely enough. So we have 4 over 1 plus z squared plus 2z minus 2z. Again, that cancels out. So we have a minus 2 here. Minus 2 over 1 plus z squared equals 4. Okay, when is that going to be the case? Well, what we can do now is we can try and solve first for this 1 plus z squared here. So let's multiply everything by 1 plus z squared. And we get 4 squared plus minus 2 squared equals 4 times 1 plus z squared. And then we can try and solve this. So 4 squared is 16 plus minus 2 squared is 4. So we have 20 equals 4 times 1 plus z squared. And that means we can take the square root because everything here is positive. So we can just take the square root. And of course we can divide by 4 before we do that. So we have a 5 here. We're getting rid of that 4. And then we take the square root here and here. And that means here we get 1 plus z, or more precisely, the absolute value of 1 plus z. We just need to make sure that this expression is actually positive. Okay. So what happens if we solve that for z? Well, let's forget about the absolute value for a minute and just solve that. We can just say, well, z is then obviously the square root of 5 minus 1, or actually, I should have been more careful here. Let's do that differently. Let's forget about that thing because I don't like to deal with absolute values. Instead, when I take the square root, I'll just say this might be plus or minus that square root. Okay? So what I have here is then z equals plus or minus square root of 5 minus 1. We'll just have to deal with 2 different cases and then find out which one is the right one later. Okay, so here we have 2 candidates for multipliers. And that means we can, of course, compute the corresponding values for the x's. Let's take a quick minute to deal with the case z equals -1. Before we go on, if we look at the equation system here, where is it? Here. Here's our equation system. If z equals -1, then what happens is this and this will be 0. So we get -10 -2 times -1. So that's -10 plus 2, that's 8. So we get the equation 8 equals 0. And of course, that can never be true. Okay, so if that is the case, then the first equation becomes 8 equals 0. And that's obviously not possible. So that case doesn't lead anywhere, and that means a choice of -1 for the multiplier is not possible in an optimum. Okay, so that case is done. We don't have to deal with that ever again. So from our z values, from these two possible values for z, we can now compute possible values for the x's, corresponding x vectors. That would then be, let's see, x star. Let's call the first one x star. We get that by simply substituting that z value into these equations here. Let me just abbreviate that computation a little and tell you what the result is. That's just basic algebra. So you get 1 over square root of 5 times square root of 5 plus 4, 2 square root of 5 minus 2. And for the second, you get the candidate 1 over square root of 5 square root of 5 minus 4, 2 times square root of 5 plus 2. Okay, so those are the possible solutions, and that means those are our candidates for optima. And now the only thing left to do is we need to find out which of these is actually a minimizer, or maybe both are minimizers. And of course, the easiest way to do that is we just compute the function value at these points and see if they are both equal and both are minimizers, or if one is less than the other. And again, computing the function value is just basic algebra. So I'll spare you that work, give you the results straight away. That would be 28 minus 8 times the square root of 5 for the first point. And the second candidate, we get a value of 24 plus 8 times the square root of 5. So you can easily see that the first point has a lower function value. Oops. Lower value for x star. Right, I have 24 and I'm subtracting something, and in the other case I'm adding something, so that can't be better. So we're minimizing, and that means this first point x star, that is our optimal solution. Okay, so we have two candidates. We eliminate one by just comparing the function values, and that means only one is left. So the only question is, does that function actually have a minimum? Maybe none of these are a minimum. And the answer would there be, yes, it does, because the objective is continuous. And we can restrict all of this to a compact set, so bounded and closed. For example, by just taking a box of, I don't know, let's say size 10 or something like that. The minimum is sure to be somewhere in there. And over that, it needs to assume a minimum, of course. and it can only be greater outside of the box. Okay, so there is actually an optimal solution, and that means X star must be the optimal solution. And if you compute that value here of that X star, then you can actually see that it is on the cycle and that it is at least close to the point that I sketched before here. Where was that? Here, right? So that is the X star. That X2 star is actually on the other side of the circle. So if we're drawing this line here, then that point, that would be the X2 star. Okay, that concludes this problem. Questions?
There are two questions. Why did we also need the actual constraints? Isn't it enough to find 0 points of Lagrangian function?
No, it's not enough. So the condition is always this Lagrangian function must be zero. So we need to find roots of the Lagrangian function, and the constraints must be satisfied. We always have to include that. Plus, if we do not include the constraints, then in this case we would get just these first two problems here, these first two equations, sorry, for the free variables x1, x2, and z. And there's no unique solution to that, obviously. We couldn't expect to get one. Right? So 3 variables means we should at least have 3 equations to get something meaningful. Even then, the solution might not be unique, but at least we can get close to that.
Okay. Next question, in what case do we have to execute Jacobi for the function hx, since Dr. Ritter, so you did not do so in the lecture?
I did not do that, and I should have done that in the lecture. I'm not quite sure about that anymore.
42.
So maybe one remark to that last question as well. Maybe that answers this as well. What you can do here is, instead of doing it like this, you can also include the constraints in the Lagrange function. And that's how I computed an example in the lecture. Maybe that helps. If you do that, then you automatically get this last line from the Lagrange function. Yeah, but just including the constraint basically as another line. So that kind of unifies this idea. The downside of this, and the reason why I'm not doing it anymore here, is this does not work anymore if you have inequality constraints. So if you need to go for KKT points, that's the subject of this week's videos, KKT points, with inequality constraints, then you can't do that anymore. But this same idea here, basically the same idea still works for KKT points, yeah, if you just add a little magic to that. That's why I chose to present it in this way.
Okay. Next question, in what would it look like if we had more than one constraint?
What would it look like if you more than one constraint? Well, basically for more than one constraint, we would have an h function that has vector values. So just for a very quick sketch, that h function would then be, let's say again, we have 2 input variables. Then that means we had some h1, h2, and so on, up to the number of constraints. Yeah.
I think he is just wanted how he can imagine more than 2 constraints.
More than 2 constraints.
More than one constraint. How he can imagine that?
Just combine that. For example, let's draw that again. So, for example, in this setup here, remember we have something like a circle. Something like this. So this is basically our constraint. The point needs to be on that circle. Of course, one thing we could do is we could just add another circle. Let's say the point needs to be on that circle and on the other circle. And of course, that's easy to solve then because there's only 2 points left. And we could just examine those 2 points and do away with all this KKT stuff. But in higher dimensions, it might not be that obvious, right? So let's say you have 2 balls intersecting in 3D space. Then it's not just 2 points anymore. Yeah, now it's something like another circle that is somewhere in this R3 space. And you have to find a minimum of a function along that circle. That complicates things a little. Or of course, if you had inequality constraints, then things also get a little more interesting, right? And that's what we're doing this week. So if you have a setup that says something like, I want to be somewhere on that circle, plus I also want to be below that line. And at the same time, I want to be to the left of this line or something like that. Yeah, and maybe I also want to be, let's do just one more. I also want to be below that parabola. Yeah, so you could have more than just one constraint. And in this case, let's see if I can find the actual feasible set. Shouldn't have complicated that much. So we need to be below the parabola. We need to be to the left of the blue line, below this line, and on the circle. So I think, no, not quite. This here should then be the feasible set. Yeah, and in this case, we have one equality constraint and 3 inequality constraints. So that's a setting that you could have even in 2D space. And in higher dimensions, you might achieve more interesting sets with equality constraints as well. We'll see examples of that, especially these inequality constraints, on this week's problem sheet when we do KKT constraints. And we'll discuss some of these problems in next week's exercise sessions. Does that help?
I think so. The last question is, why is there a factor in front of the corresponding x vector? I mean the 1 divided by the square root of 5.
Why is there? I didn't get the beginning.
Why is there a factor in front of the corresponding x vector? I mean the 1 divided by the square root of 5.
This thing here?
Yes.
Basically, I took that out.
Yeah. Okay.
Just do the computations. That's just what happens to happen here. Okay. And of course, you can write it in a different way. You can take that factor inside, and then, I mean, you could also write this like, like 1 plus 4 over square root of 5, and 2 minus 2 over square root of 5. So maybe if you did this yourself, you might end up with something like this. That's just the same thing. I just decided to take it out because I thought it looked nicer.
Okay, that's all. Oh, okay. There's another one. In the step after you wrote third step yields, couldn't we have taken
third equation yields? Yeah. Yes, here.
Couldn't we have taken the square root immediately?
So you mean you just take the square root here and here as well? Of course, you can do that. So. Yeah, you can. Sure.
Okay, that's the last question.
Should lead to the same results, hopefully.
Okay.
Okay. Yeah. If there are no more questions, then thanks a lot, Philip.
You're
thanks
welcome.
a lot for attending. I'll have the recording up sometime tonight, hopefully. And I'll see you on Thursday in the tutorials. See you then. Bye.
See you then.
Bye, Philip.
Bye.